this particular problem, it says that the work function for a silver surface is 4.73 electron volts. Part A wants us to find the minimum frequency that the light must have in order to eject electrons from the surface, and then part B wants us to find the maximum wavelength of the light beam. Okay, all right, let's do it. So in order to find part A, to find the minimum frequency that the light must have to eject the electrons, all you have to do is set up this particular function here. This is the energy coming in from the photon. I equals to the kinetic energy plus the work function. So here I'm just going to go ahead and simplify things a little bit. The wording here suggests that is the minimum frequency. Well, if it's the minimum frequency, then there is no kinetic energy because you're looking at that critical threshold value where things will barely starts to move. So because of the phrasing here, minimum frequency, I can set Ke is equal to 0. Okay, K is equal to 0 because this is just right where the electrons are about to get moving, okay, or get ejected. So therefore, I can go ahead and break E on the left side into its definition, Planck's constant times the frequency of the incoming beam or photons here, and that equals 0 joules because Ke is 0 because it's not moving yet. And then here's the work function, and the work function is given to us as 4.73 electron volts. All right, if I go ahead and plug in Planck's constant, 6.63 times 10 to the negative 34 joules per second here. Frequency of the photon is what I'm looking for, right? I'm looking for the minimum frequency that's needed in order to get these electrons to start moving, okay, or to get ejected. All right. On the right side, I just plug in W. The work function here for the silver surface given to us is 4.73 electron volts. That's what I did there. But I do want to point out that here, the unit on the left side is in joules, and the unit on the right side is electron volts, so make sure your units match up. So in order to figure out frequency, I'm just going to go ahead and divide both sides by 6.63 times 10 to the negative 34 joules just to get the frequency of this incoming photon by itself. And then I highlighted here in my work electron volts and joules. That is to help you pay attention to your units. Okay, it's important that you make sure things are either in electron volts or in joules in order for things to cancel out. So I notice that there's a discrepancy here on the top. That's electron volts. The unit here in Planck's constant that I'm using is joules. So I'm just going to go ahead and convert 4.73 eV into joules simply by doing this. So the conversion factor is that for every 1 electron volts, that is 1.6 times 10 to the negative 19 joules. And units cancel out if you set your conversion factor up carefully. So you start with 4.73 EV. And then the next conversion factor, EV has to go on the bottom because EV has to cancel out and because you want joules. Okay, so make sure you plug in the right values here. And if you convert correctly, 4.73 EV is about 7.57 times 10 to the negative 19 joules. Now that I have that converted to joules, really, I'm just going to use it. So instead of using 4.73 EV in the numerator, I'm just going to plug in 7.57 times 10 to the negative 19 joules because that's what the conversion factor is equivalent to. And on the bottom is still Planck's constant. As you can see now, joules on top and joules on the bottom cancels out. And the only unit we have left is seconds in the denominator, which can be brought up to the numerator. That becomes S to the negative 1, which is the unit of hertz. So therefore, if I simplify this in my calculator, you get about 1.14 times 10 to the 15 hertz. Okay, and so that is the answer for part A. Well, part B wants us to find the maximum wavelength of the light beam or just to eject these electrons. Well, the maximum wavelength can be calculated simply by using V equals wavelength times frequency here. Okay, here we already know velocity, we know the frequency. Therefore, I'm just going to plug it in. V here is just the speed of light because we're dealing with light here. And therefore, the frequency we already calculated in part A, which is 1.14 times 10 to the 15 hertz. And here, calculator work time. If you do it correctly, it'll give you about 2.63 times 10 to the negative 7 meters. However, you can leave it in meters or you can convert to nanometers. So if you convert this value, 2.63 times 10 to the negative 7 meters to nanometers, it'll give you a value of 263 nanometers, okay? So I'm just going to highlight 263 nanometers, and that'll be your answer. And that's it for this particular video. All right, I hope that helps. Stay nerdy. Don't be whack.